Okay, so this is about CD1 restricted T cell responses. So CD1 is restricted to T cells, and more specifically NK T cells, not NK cells, NK T cells. And as you can see, the CD1 is interacting with the TCR on the NK T cell, and the TCR receptor is presenting a lipid. Basically, we've got type 1 NK T cells which are restricted to CD1. They recognise alpha-gal Sir, but they have a limited TCR repertoire, only recognising V alpha 14 in mice and V alpha 24 in humans. And the type 2 NKT cells, which are non-classical NKT cells, they recognise CD1 A to D, but however they don't recognise alpha-gal Sir, but they have a diverse TCR repertoire. So there are several mouse models that can be used to study CD1 and lipid presentation. So here is one, mice with CD1D knockout, and they lack CD1D expression in all cells, B cells, D cells, and macrophages. And they also don't have any NKT cells, no NKT1s or NKT2. So that comes under lack all CD1 restricted T cells. Then we have these J alpha 18 knockout mice, and if you remember from before, this is the J alpha 18, and we can see that it would most probably affect the type 1 NKT cells because these are selective to this TCR repertoire. They have normal CD1D expression, but these mice lack in invariant NKT cells. CD1 tetramers can also be used to identify NKT cells. This tool allows us to set apart and identify iNKT cells from all the other T cells in the mice. It's basically a soluble tetramer of CD1. Well, it's alpha-gal Sir CD1 tetramer. And then we can label them and make them fluorescent. And if we have a pool of cells in the spleen and do flow cytometry, this will bind only to the T cell receptors on the iNKT cells. So this allows us, because iNKT cells are the only ones that can identify alpha-gal Sir, CD1D, and CD1D, this will allow us to identify iNKT cells. And so here we're looking at probably this box here. So high CD4 expression, but we want a high CD1D expression too. This is empty. This is loaded with alpha-gal Sir, and we can see that it's increased. As NKT cells are T cells, they develop in the thymus, and as T cells, they will go through positive and negative selection. But NKT cell development is dependent on CD1. So NKT cells will go through positive and negative selection and recognizing lipids from CD1D. So I think whatever lipid is presented to them will result in what they will be developed into, I think. So they need CD1 recognition in the thymus in order to develop. And this is why mice without CD1D, so mice without CD1D don't have NKT cells either, because they don't develop, because they need CD1 to develop. So for NKT cells to develop, they need CD1 and lipid presentation. They are CD1 dependent. So once they're mature, they will leave the thymus and go to the periphery. So it's leaving the thymus and going to the periphery. sorry, this is not the cells we're looking at NKT cells, so go to the periphery. So in the end, it's a bit of a gamble what CD4, CD8 expression is on the NKT cells. Mice, it can be CD positive or double negative, and humans can be CD4 positive, CD8 positive, or double negative. So concerning NKT cell development, PLZF is a limiting factor, I think. So PZF is a transcription factor, which is really important in the precursor committing to being an NKT cell. So PLZF is a transcription factor quite unique for NKT cells. Mice without it have very few or no NKT cells at all. It's highly expressed in the thymus and really important for NKT cell development. So there's actually a whole family of NKT cells that are produced, and these are cells coming out of the thymus. So similar to T helper cells, we've got these NKT17 cells which express interleukin 17 and which express raw gamma T and produce IL-17. And then we have these NKT2 cells which express PLZF and produce interleukin 4, interleukin 13. And then we have NKT1 cells which express TBET and produce interferon gamma. So quite comparable to Th1, 2 and 17. But the difference is these are maturing in the thymus and creating all these families. So NKT cells don't recirculate like B cells and T cells. They are tissue resident cells. So they develop in the thymus, then they'll go to the liver and they'll stay there. They'll go to the gut and they'll stay there. It's not known how they decide where to go, but it is known that when they get there, they stay there for life. This is basically showing what applies to both type 1 and type 2 NKT cells, and this is showing where they're divided. Okay, so both type 1 and type 2 can and do and don't express NK 1.1. They also do and don't express CD4 and CD8, and they also can be found in different tissues locations, both of them. I'll just read this out. CD4 plus, CD8 alpha alpha plus, CD8 alpha beta plus, CD4 minus, CD8 plus, double negative. CD4 minus, CD8 negative, double negative. So what makes them different is that type 1 NKT cells only recognise alpha-gal Sir. Sorry, only type 1 can recognise alpha-gal Sir. And type 1, there are many NKT cell subsets. So what we talked about before, 1, 2 and 17. But these cell subsets haven't really been studied. And I'm guessing that's because they're not expressed in mice. And just as a side note, alpha-gal Sir is really used as a tool. It's not well, originally it was found in marine sponge, and it's only recently been found in, I think, the intestine of bacteria, if they even have intestine. So I think it's been found in bacteria from the intestine, sorry. But they just use it as a tool to have a strong activation of NKT cells. So how will NKT cell activation take place? So our antigen-presenting cell or dendritic cell will internalise the bacteria and then present the lipids onto CD1. So the dendritic cell will uptake the bacteria, internalise it, and then present the bacteria's lipids onto the CD1, and then present it to an NKT cell. The lipid will be loaded intracellularly onto the CD1. it will go to the surface and the NKT cell will come. It will see the CD1 with the lipid from the bacteria, and as a result get activated. So it's quite easy. Internalize bacteria and induce NKT cell activation. And then the NKT cell will produce a lot of cytokines. And they measure NKT cell activation by the amount of interferon gamma produced. And as you can see, alpha-gal cells produce a lot of interferon gamma. But they also saw activation with salmonella. But the thing is, salmonella doesn't have lipids. So as salmonella doesn't have CD1 binding lipids, they were wondering how this activation is happening. So how were the NKT cells being activated? So as the bacteria doesn't have lipids, once it's internalized, there won't be any lipids presented on the CD1, and therefore the NKT cell wouldn't be activated, at least not by this mechanism. So there must be another mechanism, and the suggested mechanism is this release of cytokines such as R12. And what they suggest is that toll-like receptors are actually picking up signals and then producing these cytokines. And she just put this slide with a bunch of TLRs in it just to refresh your memory. So TLR5 flagellin, TLR2 PGN, TLR62 diacylated lipopeptides, TLR1 and TLR2 triacylated lipopeptides, TLR4 LPS. So self-lipids and cytokines, followed by cytokines, will be enough to activate NKT cells. So I think what they're saying is the bacteria release PAMPs, which then cause increased production of self-lipids, which were presented on these, but also increased production of cytokines. And this was Paget et al. 2007. So when we're dealing with endogenous or self-lipids, we need, because they reckon that the signal is not as strong, so we need cytokines as well to actually activate the NKT cells. So basically we have two different paths. So the theory is that endogenous lipids are constantly presented in the cells but degraded by alpha-gal A, lysosomal A-galactose A. And they reckon that TLR signaling blocks this alpha-gal A activity, leading to the accumulation of endogenous lipids in the lysosome. So here there's no microbe, and we can see the alpha-gal A breaking down these endogenous lipids, and only a few of them are being presented. But when there's a microbe present, that will cause it will bind to the TLR, and it will cause the deactivation of these alpha-gal A, which will cause an accumulation of the endogenous lipids, which will then be presented to the NKT cell, and this influx of endogenous lipid will activate the iNKT cell, and it will start producing interferon gamma.
So until this paper that came out in 2010, so basically this paper proposed a mechanism that could explain how an antigen-presenting cell that is stimulated by TLRs can induce the activation of NKT cells. So the idea is that in normal conditions, because cells have still a lot of lipids, and as we said, these lipids, CD1 will be only bound, will always have bound some endogenous lipids. In normal conditions, even though the cells will have some endogenous lipids, there is an enzyme that is called this lysosomal alpha-galactosidase A, so alpha-gal A. This enzyme will be digesting these lipids constantly. So we will always have lipids in CD1 that are not very stimulatory and are at low levels. So basically the enzyme kind of digests the whole time these lipids. When we have TLR stimulation, this will block this enzyme. So then we will accumulate a lot of endogenous lipids that will bind CD1 and will come out to the surface. Yeah? Does it make sense?
Okay, so we've got two ways into NK T cell activation. This A is just steady state autoactivity, so that's just the cell on its own. I think, I don't know why stuff's happening, but it is happening. I don't know, yeah. But what we've been talking about so far is so actually initially what we're talking about is microlipid mediated activation. Is when the bacteria is consumed and then the lipid or bacterial lipid is presented on CD1 and then presented to NK T cells. But obviously when they saw that some bacteria that they were giving, well, here we go, for example, a virus which they don't think has any lipids on it, they don't understand why there is, activation of NK T cells. So what they think happens is the virus causes a lipid synthesis disruption and like an influx of self-lipids which are presented, but then it also causes an increase in cytokines. So we've got this self-lipid mediated activation, so we've got this and this interleukin 12 happening at the same time, and that's another way to activate NKT cells.
Cells activated, so what does it mean? What are the functional consequences of all this? How the immune response is affected by all this? So basically, the main function or the main feature of NKT cells is that they can produce cytokines, and they can produce a lot, and they can produce it very, very, very quickly as soon as they see a lipid. So basically, when NKT cells get activated, they secrete. Actually, in a couple of hours, they are already secreting cytokines, and this is why they are sometimes say that they are kind of innate cells. So they are in the middle between innate and adaptive, because they do have a T cell receptor, so they are a bit adaptive, but they are really, really fast when they respond. So this makes them a bit of a innate cell. So the secretion of cytokine means that NKT cells can modulate the function of many other cells. And let me just show the next one. Okay. And they can do that either by secreting cytokines, as we said. They produce a lot of interferon gamma, for instance, and this can function on other cells like NK cells. They produce IL-4, or as well, because NKT cells, as we say, they can interact directly with other antigen-presenting cells and modify their function by direct contact. And this is the case, for instance, they can interact with B cells and regulate the production of antibodies, or regulate dendritic cell maturation, or interact, for instance, with epithelial cells and regulate the production of IL-10. And, well, we will see later, but this is important for intestinal inflammation and inflammatory bowel disease.